Ben voilà, le titre est en français, mais I'll switch to English right away for the remaining of the talk. I'll present you a collaboration that I've done with Marie Sabre, Klaus Hermann, both at Université Sherbrooke, and Marius Hofer at the University of Hong Kong. So I'll start presenting some theoretical results that we've had towards the distortion of copula models. It started years ago with a collaboration with Nahid. We started working with Klaus on distorted copula models and a specific type of distortion of distorted copulas. So I will introduce this and then give some general results and then more precise results for extreme value copula models and also for extreme distortion functions. And some applications then following from those results on multivariate risk measures, and then the application on hail storms in Alberta. So what's a distorted copula and its domain, max domain of attraction? We can define, so D is a function, distortion function, if it's a distribution function that is equal to 0 at 0 and 1 when evaluated at 1. So distortion modifies the probability measures, and it is used a lot in insurance and in finance and in quantitative finance. So we've started using it for insurance premiums and then for capital allocation as well. For a non-negative loss random variable L, a distorted premium is the expectation under this new distorted distribution function. So it reflects a risk attitude towards a specific risk. And so what we've been thinking of is, well, what happens if we have that distortion, and how could we find some nice results on multivariate distributions? So we decided to use copula models. Copulas now are well known in the Quebec region, I would say. And we're using these copula models in order to have an interpretable way of studying multivariate models. So Slar's theorem says that we can express a multivariate distribution function as a function of its margins. This way we can allow for a marginal representation and have this nice structure for the dependence. And there are a lot of very nice properties, and it's been studied for years. So what we thought is, what happens if we want to have, if we want to distort those copula models? So the Morilas type distortion is a distortion function which can be expressed as a distortion of the copula of the inverted distorted margins. So to be able, so sufficient conditions to ensure that it remains a copula model is that the copula is, if the distortion function is the absolutely monotone surjection. And so what that means is, if we have a D absolutely monotone, then it's continuous and convex if we're in a bivariate setting, and for greater dimensions, has non-negative increasing in convex derivatives of order up to E minus 2. And if we have absolutely monotone, because we'll also need this property a bit later on to ensure other nice results, it means that it has derivatives that are always positive, no matter what are the orders. So we could say that it is a bit more restrictive if we're asking for an absolutely monotone, and a bit less restrictive if we want to have the absolutely monotone. And this way, if the distortion function respects this condition, then we can ensure that the distorted copula also remains a copula. So so the distortion of copulas. One example is the Archimedean family. So we can show that an Archimedean copula is a distorted independent copula. Archimedean copulas can be expressed through a generator. So this is the definition of an Archimedean copula. And we can show that if we use a distortion function that is expressed like this, then we can see that this copula also remains, and the Archimedean copulas can be expressed as independent. So another example, here what we show is if we distort, so let's say we have a normal copula and then we use this power function to distort the normal copula, then we end up with this blue dashed line. If we distort the Clayton copula with the power function, we end up with, again, another different type of distortion. And for the Gumbel copula, if we use the power function, we see that the non-distorted copula and the distorted copula model are the same. Why is that? It is a specific case of this power function and the fact that the Gumbel copula is max stable. So we say that a divariate copula C is max stable if it can be expressed like this with this relationship. So if we do just the quick example with the formula, we can have that the Gumbel copula can be expressed if we distort. With the power function, we can retrieve the initial Gumbel copula definition. So it's only possible because it is max stable, and we'll see that it is the case if we use the power function as a distortion function for all extreme value copula models. Now what we want to do is to understand the asymptotic behavior of a distorted copula model. So we will define C star, an extreme value copula, if there exists a copula C such that this C n of each margins to the power of 1 over n converges to this C star as n goes to infinity. So we say that C is in the max domain of attraction of C star, and write it like this for the remaining of my presentation. Other definitions of extreme value copulas are also available through the spectral measure, Pickens dependence function, stable tail dependence function, tail copulas. So we can see other types of definitions. What we use here is we try to see what's the limiting behavior of this distorted copula model. So either in the extreme value setting, but for all distorted copulas that respect the distorted Morila's distortions. So if we have this stabilizing sequence of Rn, so for a rate function Rn, which is non-decreasing and goes to infinity as n goes to infinity, we can have, so if we have this Cn, from which we want to see if it's a max, well, we want to establish a max stable copula model, then we can take the distortion by the definition of the Morila's type of distortion function, and then introduce, so we can add this Rn and this 1 over Rn. That doesn't change anything here at first, but then it helps simplifying and then obtaining our max stable copula model. And the distortion, so Dn can converge to a distortion D star, so to the limiting behavior. Same way, C, the copula converges to C star for the right choice of this Rn, this stabilizing sequence. So the main theoretical result that we establish is that we denote by C copula of D dimensions, and C is in the max domain of attraction of C star. Then we take a rate function Rn, which is non-decreasing, goes to infinity as n goes to infinity. And the absolutely monotone and surjective distortion function such that we have, again, this equality that the limiting behavior of Dn goes to D star. Then we have that the copula, the distorted copula CD, is in the max domain of attraction of C star, D star. So we have the pointwise convergence. We can say that we have a copula that's in the max domain of attraction of C star. We have a distortion D that also converges to this D star. Then we say that C star, D star, CD converges to C star, D star. And D star is of that specific form and no other form than that. And we can also show the other way around, that we can retrieve CD if we start from C star, D star. So that's mainly what the theorem says, but in a figure. So if we start with the copula in the max domain of attraction of C star, and then we have D star, we reach this C star, D star, and we can also distort the copula model first, then obtain the distorted copula model, and find its max domain of attraction C star, D star. Now, how hard is it to find a distortion function that meets these assumptions to have this D star? Well, we can see some different classes. We will see some different classes of distortion functions. It's more or less restrictive, depending on what's your definition of restrictive. But if D is absolutely monotone, we see that D can be expressed as the probability generating function here. So the probability generating function of a discrete random variable n. And additionally, D is a distortion function supported on 0, 1. D0 is equal to 0, and it means that the probability of 0 is equal to 0. So all this kind of makes sense, and we can find now probability generating functions that can be taken here for the Mohilas type of distortion. So we have the Poisson, geometric, and zeta. So those are distributions of random variables from which we can take the probability generating functions, which can then represent our distortion function for our copula model in order to get a distorted copula. What we can think of if we want to have, if we want to respect those assumptions, we find that the max domain of attraction of a Weibull distribution. So if this distortion function is in the max domain of attraction of a Weibull, and if it is regular, well, D is in the max domain of attraction if it is regularly varying near the upper endpoint of its support with index gamma, and then we can establish that we have the same functions that are in 1, 2, 3 here are respecting these definitions. So we can use those to have this limiting, to find this limiting behavior of a distorted copula model. We want to know also, we can ask ourselves, okay, so if we have a copula model and that's in the max domain of attraction of a C star, and we have a distortion function that's in the max domain of attraction of D star, well, how will I have a different copula model if I have already things that are converging to a specific distribution? So we ask ourselves, do such functions distort the limiting copula C star, D star? And what would be the limit if we use the stabilizing sequence? So we have that D be an absolutely monotone distortion function such that the derivative is finite, which means that D is in the max domain of attraction of a Weibull distribution. We'll also see specific cases where we have different values for the, for the parameters. So let D be a distortion function such that it's in the max domain of attraction of a Weibull. Then there exists a rate function Rn such that we find the limiting behavior, which will be equal to exactly what we were looking for, which is the only way we can distort copula model to follow this Marila's type of distortion such that it remains a copula and we can find its maximum of attraction. So we can find that the only function, so the only rate function we can find is expressed as this guy right here. Now, what does it do when we apply real examples or distributions or distortion functions to those copula models? So first, if we use the zeta distortion as an example, and later on with the application to hailstorms, we'll see what happens with a geometric distortion example. So let n follow a zeta. We have the probability mass function equal here. And the expected value that is finite for s greater than 2. And when s is between 1 and 2, we have an infinite expected value. So this makes things a little bit interesting in the way that we will find different distortions depending on the value of the parameter s, because we have that we need to use the probability generating function in order to have our distortion function. And this distortion function will depend on s. So as s stays in the bounds or goes out of the bounds, we will have a different distortion of the copula model that we find. So now let's apply this. What we did is to calculate the different distortions, and we found that the limiting distortion, if s is greater than 2, when we have a finite expected value, then we have the identity, which means that our copula is not distorted. However, if we have s that is in between 1 and 2 here, we have another distortion, we have another result, which means that our copula model will be distorted. So the limiting distortion function d star is in the maximum of attraction of that label, but it depends on the value of s. And it shows that the infinite mean of m can alter the domain of attraction of the distorted copula C. So here are some level curves. We can see that with the normal copula, so level curves of a normal copula here, distorted by the zeta probability generating function, and its limiting independent copula C star here, distorted by D star. So an extreme value copula here on the right-hand side and non-extreme value copula here, we can distort them anyways with the zeta. And for S, in this case, S is between 1 and 2. So we have an infinite mean, which means that we have a distorted copula model in both cases. Now, what happens if S is provides a finite expected value? Same thing, but with a different value where we have a finite mean. Then the normal copula is distorted here, but much less. And we have that the independent copula, which is already a C star, doesn't change at all. So we find this identity. Okay, so with those results, we wanted to have some applications and figure out, okay, so now what's the impact if we work with insurance capital requirements, and most of the time to calculate those, then we use multivariate or univariate risk measures. Now in this framework, we opted to illustrate our results on multivariate risk measures. First, for the tail dependence, so the upper tail dependence coefficient lambda u and the lower tail dependence coefficient lambda L. So we have this probability that a random variable will exceed a specific value as the other one also exceeds this value, and we push this limit to 1 for the upper tail, and for the lower tail is the probability that it will be smaller than u, knowing that the other random variable is smaller than u, and then we have this limit when u goes to 0. if you don't know yet. So these coefficients give us a lot of information, usually in insurance, to have an idea of what's the relation specifically for heavy-tailed risks. So we just here provided the corresponding distorted results with respect to the non-distorted copula model. So if we distort a copula model with D, that's in the max domain of attraction of the Weibull, then we can, of parameter gamma, then we can find the upper tail dependence coefficient with the lambda of the copula that is not distorted to the power of this gamma, this index. And same thing, we have an equivalent result for the lower tail dependence coefficient as well. So, well, and this is just to make sure that we will never get an upper tail dependence that will be smaller than 0. And it is because D, by definition of D, it is too absolutely monotone. So it also ensures that this will be respected. So multivariate value at risk. What we use now when in insurance, when the insurance company doesn't want to aggregate the complete portfolio, but consider still dependent either risks or business lines or clients, then using the joint distribution and finding the level curve and then deciding, so this would be a level curve such that it has a probability, a CDF that's being equal to 0.95, for example. So this alpha level curve, in this case, it's 0.9. So it ensures that both risks in a bivariate setting have a CDF equal to this 0.9. So this line is all the combinations possible to achieve this CDF being equal to 0.9. Now, what we do, which points should we select out of that line? Lots of different ideas have been suggested in the literature. And one way is to select the smallest sum of the components, such that the insurance company would have to set aside the less possible money to ensure that this level is being reached. Other ways, these two dots would be the value for X and the value for Y to set aside such that it respects proportional allocation compared to the total risk protected. So different ways. The objective here is not to discuss necessarily why would one use one or another, but more to say what happens when we distort those on the complete level curve. So this is when we use the value at risk. Also, what happens if we use a tail value at risk, which is now well known, so an expected shortfall. It's a multivariate definition of the tail value at risk, or expected shortfall, or conditional value at risk. So we take the expected value of the random variable, knowing that it has exceeded its level alpha, or the robust or a range value at risk, which gives the option of having an upper bound as well, such that if you have a reinsurance contract, or if you have other, say, other assets or other conditions that makes you want to have this upper bound on the distribution, or if you have a very heavy tail distribution as well, you might want to cap this. So it takes the expected value of a random variable when this random variable is in between two bounds. So let's say the 90th quantile and the 99th quantile, and takes the expected value in between those bounds. So those are the VAR, T-VAR, and R-VAR are three risk measures on which we applied our results. So we can see here that for the T-VAR and the R-VAR, so now we have this lower Horton's VAR that we had previously at level 0.9. Then the T-VAR is expressed with this blue line here. So it's makes sense that the expected value will also be greater, always be greater than the quantile itself. So we take the expected value of all possible values above this quantile. So it gives another value, which is more conservative from an insurance perspective. And the range value at risk is in between because we don't take all the values up to infinity to the upper support. We just cap to alpha 2. In this case, it's from 0.9 to 0.975. So, well, theoretically, what we did was to study what happens at the distortion on the level curves, so on the var, and then we could transfer this result because, as you can see here, they all depend on the value at risk, which makes sense because those depend on the quantiles. So if we have a two-dimensional copula, the associated level curve will be expressed. So P is the level alpha that I named alpha previously, the 0.9. So at the level P, we have a level curve that defines such that if we evaluate the copula model at both levels, we will reach this P level. So what we say is, let's say you pick any point on the curve, you find the corresponding value of U to respect this initial level P. So for a distortion, a D strictly increasing to absolutely monotone distortion function, continuous at 1. The level curve function can be expressed as a distorted level curve of the non-distorted copula model times the inverted distortion function. So it's quite nice to have those little formulations which help us calculate straightforward not the numerical result, but the theoretical results. And then we can express, so we can also show that this holds if we evaluate the way we defined it here, we can retrieve the level P. Now what happens when we use the level curves and the copula, the distorted copula models? For the R-var, we can find an upper bound. That's nice. So it tells us that if we have lower Orton R-var, we find a lower bound here that says, okay, an upper bound, sorry. It will never be higher than that value. Well, it's okay, but we know that for a CDF, a regular CDF that's not expressed with a copula model, we can find both by lower and an upper bound if we have a multivariate CDF, so a joint distribution, not expressed by means of a copula model. So what we figured is, okay, so now what happens if we want to go the other way around and using Sklar's theorem, try to fall back on our multivariate model to see if we can get those two bounds. Also, another reason why we want to do that is once we distort, so if we have a copula model that's distorted, it happens, and we've worked very hard to try to figure out an ordering of the lines of our level curves, and sometimes they cross, sometimes they don't. We weren't able to find a way to formalize when they cross or when they don't. So that's why then when working with multivariate scarce measures, we said, okay, so let's do the backward process to go back to the regular multivariate CDF. So in this case, if our goal is to generalize univariate distortion effects to shift level sets upward, the modulus transformation alone is not sufficient. So for a D absolutely monotone distortion function, D continuous at 1, we could apply the distortion directly to the joint CDF. So here's what we suggested. So now what we can find is if we have the copula model that still gets curves that are higher, they cross or they go lower, then if we transform this into CDF, we find a way to be able to describe when they cross, if they cross, and what happens. So it gets a bit easier. And in this case, what we can see is if we have D that's two absolutely monotones such that the density du is smaller than a value D, then we have the following bounds. So we have a lower bound and we have an upper bound that depends on the value. Okay, so we find that, for example, with a geometric probability generating function, it's 1/p, the upper bound. And this way we can then fall back on the same results we have with multivariate distribution functions. So we can find a lower bound and an upper bound for the range value at risk. So that was kind of a nice application on multivariate risk measures. The process to go from a level curve to a distorted level curve or to a copula model to a distorted copula model is all in here. So if you start with a level curve and then you change the margins, if you change the margins and then join them through the joint distortion function, you can fall back on the joint distortion distribution function. If you use modulus transform from C to CD, which is the very first definition I presented when we have a copula model, and we want to express it through the modulus type of distortion function, this D of C of D minus 1. If we do this and then work with the distorted margins, we end up with distorted level curve that we want to work with. So no matter what we use, we can still very easily go from the distorted copula model to the distorted joint distribution or the other way around. Now the simulation of a distorted copula model. We have this very nice sampling algorithm. So sampling modulus transform copulas for absolutely monotone distortion functions D. If we have du that expressed as the same way we defined our proper, the ones that worked in our case, the distortion functions. If it's an absolutely monotone distortion function continuous at 1, where this pk is greater than 0, and we have the sum of all the probabilities that's equal to 1, what we first do is sample k from that probability, so from that distribution, that function that we are using for the distortion. And then once we sample k, we sample u1 to uk that follow C, our initial copula model, independently of k. And this is very important in the proof in order to show that we're able to have this distorted copula, this simulated distorted copula model. So now, okay, we sample k, and then we sample u1 to uk that follow the copula model that we have initially, and then it returns what we take is the maximum of each column, and this vector will give us a sample that will be following our distorted copula model. So if I repeat, we sample k, so we have k samples of copulas that all follow the same C. And then by taking the maximum of each column, we get a sample of our distorted model. And why does that work? Why does that work? Because, and it's very nice because we can simply show here that because they are independent, so we have this maximum value of each column that's being taken, we can simply invert here. And since they are independent, we will be able to multiply their products and then end up with this distorted copula model. So it's really clever, and it's really nice to have this because it helped with our application that we did on the hill, and it's also very easy to compute. So if we have a normal copula sample, and if we reuse this zeta probability generating function with S being equal to 1.5, which is the case when we had an infinite mean, which means that we would have anyways because it's a normal copula, but we will distort our copula model. So the normal copula simulation, and then distorted with this zeta distortion function. So great. Application, what we had were data from hailstorms. Oh yeah, I'll just present maybe a little bit. What we had were data, and we still want, because we're not actually absolutely done with that project. We're working on doing a model to quantify the frequency of hailstorms in Alberta. So we have data from an insurance company with different with number of claims years after years, and we have approximately 20 years of data. What we did was to first have this zero inflated negative binomial, and we fitted each zero inflated negative binomial with this. We chose 5 different covariates in order to model this parameter of new parameter of the negative binomial. So we did a lot of manipulations, and we did a lot of different things with the data in order to have this proper representation of the frequency, because the insurance company doesn't have like all the data, doesn't have necessarily all the data of the hailstorms. It has the data of where clients made claims. So this is why we first used the zero inflated as well, because we had a lot of zeros. We also simulated other data to help us with this project. So we had 1,417 grid cell locations. Oh yeah, it's from 2002 to 2019. So with those margins, what we did is to use nested copula. So nested copulas are mainly, we have this first copula that represents the complete dependent structure throughout our subcluster. Well, we will have clusters mainly. What we did is a clustering algorithm to have k child copulas. So we had different clusters, and then those clusters are mainly regrouped to a parent copula C0, or parent or root copula C0. We have CJ that are the child copulas, and we have K clusters. I'll explain next how we did the clusters. And CJL are the sub-child copulas under CJ, joining a group of marginals U. And U are the margins that follow the zero inflated negative binomial. So here the idea is to divide the region. What we used is this SPAM algorithm. So important things, because at this point, what we wanted to do was to build this nested model, but also to compare and see if a distorted model would be more appropriate than a regular copula model. So first, we compared different Archimedean copula models to make sure to see which one fitted best. We used the MLE for subclusters, and then we evaluated with AIC, and then we chose the best model. Ensuring that each hierarchical structure remains in the same Archimedean family was also very important to ensure this nested structure. And this is a restriction part of the nesting condition. Then we fitted the D copula, and what we needed to ensure, again, to make sure that it was a proper copula, was that every child copula needed to have a weaker dependence parameter than the subchild. So the higher you are in the hierarchy, the smaller should be the dependence, or the lower should be the dependence strength of your model. Whereas as you go deeper for the subchilds, that's when they had the higher dependence parameter. So this we needed to ensure, and we needed to ensure that they stayed in the same family of copula. So this is what we did. Yeah, as I just said, so as you can also see, it reduces flexibility in the family selection across nodes, but it ensured that we stayed in the nested Archimedean copula, and it would preserve the copula properties. So we ended up with 34 clusters. And so our first model, C0, is independence, nearly independence. We tested different ways, but since we had this restriction also that says that we needed to have a weaker dependence strength, higher the level we were, led to that result as well. So yeah, we ended with 34 clusters, and I believe that the algorithm let us go up to, well, we used the built-in PAM clustering algorithm, and we could have, I believe, up to 38 clusters. So this PAM procedure, we used actually the importance, it gives importance to either the spatial distance or to the candle's tau. So we give a weight from which we believe the importance we should have assigns to either candle's tau or the Euclidean distance between the different clusters. And then the algorithm with this distance could help us choose the different clusters in the end. So as I said, we used MLE for each subcluster, and we could find that this is the figure of the 34 clusters we ended up with. And for us, it kind of made sense when we saw the data we had. And as you can also, well, think if you've heard of different hailstorms in the past, there are very specific areas where we know that there were, because maybe there were somewhere else, but we don't really care as long as there is no insurable damages or insured damages. Also, as I said, what we wanted is to test if a regular copula nested structure was doing better than a distorted copula structure. For 6 clusters, we had a better fit with a distorted copula model using this geometric distortion. So mainly what we did first is to have this zero inflated negative binomial fitted to each one of our margins. And then we had the clustering using this PAM algorithm. Once we had our clusters, we proceeded to the fitting of a copula. Then we evaluated the distorted copula model to see if the fit was better. And then we simulated the joint distribution and could proceed to spatial interpolation of aggregate values. So this is just a comparison with one other model here, our nested copula model. So if you can see out of sample, so after 2020 are the red dots. And we have this, the exposure in black. So we can see that the map for QINLA, this is the latent Gaussian simulation, and this is with our nested copula model. We can see that the pale areas are more at risk here, which also well, it's not very clear on the figure, but we can still show that we had a pretty good fit compared to the QINLA model. So And we also expected that near Calgary and Edmonton, it would be a bit more pale, whereas with the INLA model, that's not very clear. So that's kind of where we are so far. If we zoom in on Calgary, we can see a little bit better here. So we have, again, these maps which show that where hailstorms happened, we really had a better fit near Calgary. So in conclusion, what we did was to study the max domain of attraction of this Marilla's type of distortion distributions, and then sufficient conditions for the distortion to distort the limiting copula, the tail dependence coefficients with respect to the original copula model, bounds for copula-based risk measures, simulation algorithm, and potential application in stress testing, modeling, and dependence. Thank you.
Merci beaucoup.